Hello, everyone, and welcome to a sunny KubeCon 2025 in London. I hope you are having an amazing day of learning today. Many times we see bigger impacts or greater results achieved from small, well-executed things that are put creatively together. And today I want to highlight one such small, less appreciated and talked about, but extremely powerful Kubernetes feature, that is the init container, and share how we at Yelp leverage init containers to reduce the operational overhead of our Cassandra clusters and enhance the engineering efficiency. So introducing myself first, I am Mohammed, a tech lead in the database reliability engineering group at Yelp, where I primarily look around the NoSQL databases, and in particular Cassandra. Here is what we will try to cover today. I will try setting up the stage by sharing some information about the background in which we operate and give you a bird eye view of how we use Cassandra at Yelp. Then we'll dive into three different problems that were solved by init containers. The first was about cluster scaling. And here we will specifically be looking at the horizontal cluster scaling aspects. Secondly, I will talk about the Cassandra cluster upgrades and the impact init containers had in making the overall upgrade process easier and smoother. And thirdly, I will touch on the cluster recovery aspects from backups. In the end, I will try wrapping up some key takeaways for you so that init containers is easier for you for your use cases. So starting off with the context, how many of you have heard about Yelp? Can you raise your hand? Yeah, that's quite interesting. Those who don't know, Yelp is a community-driven platform that connects people with great local businesses. And millions of people rely on Yelp for the useful and trusted content about the business information, reviews, and photos to inform their spending decisions. As of December 2024, there have been 308 million cumulative reviews with 29 million average monthly unique users in 2024. So here is another question. How many of you have worked with Cassandra or have heard about Cassandra database? Okay, so again, those not familiar, Apache Cassandra is a wide column distributed non-relational database. And how we use it at Yelp. So if you visit any Yelp page, there will be some portion of data that is served by Cassandra. So you can imagine how extensively Cassandra is used at Yelp. So we manage over 70 clusters in production environments for different use cases. And there are more than 1,000 Cassandra nodes in those clusters. And with respect to data volumes, these clusters store several hundred terabytes of data. But it's not only about the size. Some of these clusters are highly latency sensitive, and we ensure a sub-10 millisecond latencies for read and write traffic from these clusters. From operational perspective, all of our Cassandra clusters run on Kubernetes. That's why I'm here. And this was a transition which we made around 5 to 6 years back. We used to run the entire fleet on Mesos. At Yelp, we use an in-house platform as a service called Pasta that provides the necessary abstraction on top of Kubernetes for managing different services. We run our own custom Cassandra operator that handles all the Kubernetes interaction for the Cassandra clusters. Now, the configurations at Yelp are managed in a declarative way using a central Git repository, which we call Yelp solconfig, as shown in the diagram. Any updates to these configurations are then converted into a Kubernetes custom resource. Here, the operator is continuously watching this custom resource, and as soon as it detects a difference between the actual and the desired state, it reconciles and it takes action to reconcile and convert it into relevant Kubernetes resources. We use persistent volumes as we are talking about the stateful workloads, and these are attached to the Kubernetes pods. One important thing to note here is that our clusters are spread across multiple data centers in multiple regions. So within a single data center, we maintain a replication factor of 3. However, for simplicity, in the upcoming slides, there may be a single replication setup shown. So jumping to some basics about Kubernetes pods. A pod is the smallest deployable unit in Kubernetes. Essentially, it's a group of containers that share the same network and runs on top of the same Kubernetes node. So when a pod is scheduled, all the containers start in parallel, while there isn't any strict limitation on the number of containers that you can define inside a pod. But from management perspective, you can think that it could become complex if we have too many containers inside a pod. So now there can be cases where we need to perform some certain steps before these containers starts, and that's where init containers comes into play. So these init containers are specialized containers that make sure everything is set up before main application is running. However, few key differences here. Firstly, unlike main containers which run in parallel, init containers always run sequentially one after another. And secondly, an init container must run to completion successfully before either the next init container is invoked or the regular container starts. And similar to the regular containers, there is no strict limitation on the number of init containers that can be created. And thirdly, init containers are designed for setup tasks only. They are not designed to serve user traffic. So that's why you will not find readiness and liveness probes supported in init containers. So jumping to our application of init containers and solving different use cases, the first problem is about horizontal scaling of Cassandra clusters. How scale-up works in Cassandra: when a node joins the cluster, there is a seed node with which this newly created Cassandra node interacts to learn about the cluster topology, how many nodes are there, and the token range assignments. Once this new node knows about the cluster, then it enters into a bootstrap process where token ranges are assigned to it, and then it starts streaming data from its peers. And this process can take some time depending upon the volume of data that it needs to stream. So once this streaming process completes, the new node joins the cluster and becomes ready to serve user requests. So far, everything looks simple and works fine. But the challenge we face is when we are scaling a Cassandra cluster which has change data capture enabled. Change data capture is often acronymed as CDC, which is a way to detect changes in data and allowing it to convert it into a stream. How it works under the hood is that each time a write is happening on a Cassandra cluster, a Cassandra internal will create a commit log file that contains information about the change, whether it's an update, delete, or insert. When CDC mode is enabled, something extra happens where this commit log gets replicated into another special CDC raw directory from where independent consumers can read those commit logs and process according to the business needs. In our case, we publish these events into Kafka, and from there we ensure that the downstream system gets synced. Now, CDC is controlled by a configuration property called CDC enable that determines whether this mode is active or not. Now, the problem arises if we are bootstrapping a new node with CDC enabled. So the bootstrap data will also be emitted into Kafka because CDC events will be generated for it. Now, this can lead to unnecessary duplicate events, and we may have to spend some additional cycles on the deduplication front. Additionally, the bootstrap process also becomes slower because Cassandra has to perform some extra operations for all the data that it is streaming. This makes scaling with CDC enabled more complex and time-consuming. How we solve this problem, we used the init container. So as soon as an increase in replicas is made in Kubernetes stateful set, a new pod gets scheduled and is assigned to a Kubernetes node. And then we start an init container. But before jumping on the actions of the init containers, a few things that needs to be considered here. As we mentioned previously, that streaming of this data can be time-consuming, especially for large clusters. So we need to minimize the disruptions. And at least what we can do is that we can eliminate the voluntary disruptions. This can be done by appropriately setting the max unavailable property in the pod disruption budgets. At the same time, not all disruptions can be eliminated. So there is still an involuntary disruptions that can happen anytime for many different reasons, like due to hardware failures, network issues, etc. So this means that we should be prepared. The init container code should have some preparation to handle those cases as well. Another thing to consider is that each time a pod restarts, the init container will be run. So the init container code should be only invoked when it's needed, and it should be idempotent as well. So in order to ensure that within the init container, we first check whether the node is already bootstrapped or not, so we don't do restreaming again. A simple way of doing this is by checking presence of data on the attached persisted volumes. If streaming got interrupted previously by any hardware failures or any other disruptions, we don't automatically handle it for this particular use case. Instead, we let our on-call person to reset the storage and make a decision, because such events in our experience have been rare. Next Cassandra process is started in init container, but with CDC disabled. So any data that is streamed from the peers, it will not be streamed into Kafka. Now, you might be considering that any new writes that are happening at this time, they might be lost. But because we have a replication factor of 3, so even if one node is not processing any data, it means that there will be another 2 that are processing the same set of data at the same time, so none of the data gets lost. And we have some readiness script that indicate once the streaming is complete and Cassandra is ready to serve the traffic so once we get a green signal, Cassandra has joined the ring, we stop Cassandra process gracefully and exit the init container. The reason why graceful stopping of stateful workload is important because any abrupt termination can lead to data corruptions. So once we exited from the init container, Cassandra started back in the main container, but with CDC enabled. From this point onward, we start processing these CDC events in the CDC raw directory. And in this way, careful usage of init container enabled us to horizontally scale the cluster without much human involvement. Along with that, we also have less duplicates, and the scale-up time also was reduced. The second case where we used init containers was Cassandra upgrade. This was a project we did last year when we upgraded our entire Cassandra fleet from 3.11 to 4.1 version. However, there were two challenges faced during the upgrade. But before talking about specifics, some terminologies to explain here. So typically from operational perspective, node tool status command in Cassandra helps you view the state of different nodes inside Cassandra cluster. And the output of node tool status, the first alphabet here determines the state of the cluster, whether the node is up or down. And the second alphabet tells whether the node has joined the ring or not. So there can be many states, but a few of them just discussing, like UN means that it's up and normal, and DN refers to the node is down, but it has joined the ring and it was normal. So for the upgrade, we followed the standard rolling upgrade process, upgrading one node at a time, but this failed for us. And more technical details about why it failed is being captured on the Jira ticket in the open source community. But I would try to explain the problem with some smaller examples. Let's consider that we have a 3.11 Cassandra cluster with 3 nodes having X, Y, and Z in the last octets of their IPs. In our environment, we don't use static IP assignments. So as pods are restarted, the IPs can change, and each time it's assigned whatever IP is available in the pool. So as shown in the diagram, the Cassandra node with x.x.x.y IP after the upgrade got assigned IP x.x.x.a. The problem that happened is that new upgraded node wasn't accepted as a replacement by the peers that were running 3.11 version. And this was because there was some exceptions that happened during the gossip exchange mechanism. So we did some more experimentation, and then we observed that if both IPs and version, they change together, the upgraded node is not recognized. But if we can make these two things change gradually, the process would work fine for us. So as part of this solutions, we leverage the init containers to make it gradual. And so this is the last state of Cassandra nodes prior to upgrade, with the version running 3.11 and IP is x.x.x.y. After a restart of pod during the rolling upgrade, a new IP gets assigned to the pod as soon as it is scheduled. So however, here we start Cassandra first with older 3.11 version in init container, so that the peers can recognize that this new IP is replacing the older one. So only one of the attributes gets changed. We wait here till Cassandra node is ready to serve the traffic, and then we gracefully terminate this workload and exit the init container. Then later, we started out Cassandra with 4.1 version in the regular container. Now, because the network stack is shared, the IP assignment doesn't get changed across containers. It remains consistent. So in this way, once this new node was brought back up, it was successfully joined the ring, and we had a consistent node tool status everywhere. So you can think that how careful utilization of init containers, we were able to upgrade Cassandra nodes seamlessly. And we followed this procedure for our entire fleet with 70 plus clusters and more than 1,000 nodes in them. The secondary problem that we faced during upgrade was related to SS table format versions. So The table format versions can change with Cassandra versions. In the table, you can see that there is an NB format in 4.1 version, which used to be ME in the 3.11.13 version, and similarly, it used to be MD and MC respectively in earlier 3.11 versions. So usually, from read perspective, adjacent major versions support reading from older SS tables, but there aren't any performance guarantees around it. So it's recommended as soon as you upgrade it, upgrade the node, upgrade the SS tables as well. In pre-4.x versions, we always have to invoke a node tool upgrade command. But with 4.x versions, there is some automated ways. But the problem with those automated ways is that you have less control on how many nodes the upgrade SS tables would be running. So there can potentially be some disk pressure created, because when we are running upgrade SS tables, each SS table gets rewritten into the newer format. So in some cases, you may want to run this in a controlled fashion. Our solution was quite similar to the previous one, relying on the init containers. We triggered the upgrade SS table process by a spec change in the Yelp SWA config that gets converted into a custom resource. The operator then makes the stateful set change, and then the pod gets restarted in a rolling fashion. So the first thing when the pod gets started is we start out init container and check whether there are old formatted SS table versions present or not. If not, we exit the init container, else we start Cassandra process and wait for it to become ready. Once the Cassandra process is ready, we upgrade the SS tables until it completes. Now, this process can also be long running, depending upon the amount of data that is present on the disk. And once everything gets complete, we exit the init container and start Cassandra as a regular container. Again, we ensured idempotency. If a pod is terminated, it should have capability to resume. So this approach helped us in limiting the disk pressure to at max a single node. And everyone loves seamless upgrades, and init container ensured that it was the case for us. The last case I would like to talk about is recovering cluster from backups. We use Medusa, which is an open source tool for copying SS table formatted data on disk to S3. And the picture on the right side shows the architecture of Medusa. So in addition to the SS table files, there are some manifest files that contains metadata and information about, like the timestamp at which backup was taken, backup type, etc. In our environment, we support both the full mode and differential modes, but we try to leverage differential one as much as we can. So this backup process runs periodically in a sidecar in our case. When we want to restore a cluster, we configure a new Cassandra cluster with some additional properties that lets us know about the cluster and backup, as shown you can see on the slide. So the backup identifier is the timestamp in our case at a minute resolution level. So based on these properties, a new Cassandra cluster gets created, then init containers are started, and in those init containers, we pull data from S3. If we follow a sequential approach, one node at a time, it would take much longer. So we expedite things by making use of parallel pod management policy that allows all pods to come up in parallel and start pulling data from S3. And once all nodes have completely pulled data onto the disk, we exit the init container and start Cassandra. And once all Cassandra nodes are up running in regular container, they join together to form the cluster. So in this way, we ensured our restore process is fully automated. But the requirements of disaster recovery is quite unique. Uh, you, the process is usually rarely needed, but when it's needed, there is urgency. You don't have time. So we built some automation around the init containers to ensure that our process always remains functional. Yeah, this moves us to our conclusions. As you can see that init containers are quite handy for real stateful workload applications. A few takeaways here. The first one is about ensuring that init containers should be idempotent. Any failures that can happen anytime and for any reason. So you need to make sure that there is some failure mode handling. Also, init container code can get launched each time when a pod gets restarted. There can be potentially two cases. Either you want to run init container code every time the pod restarts, like setting up a network or something similar to it. Or the other case could be that you run the init container code based on the persistent state on the disk. In our case, all of the examples that we discussed actually were related to the later case. So whenever we don't want to run init container code, we should be handling it inside the init container so that it can quickly exit. Another takeaway is minimizing the disruptions. So if we treat disruption as a process rather than an event, so it means that we can have some degree of control over it, at least on the voluntary disruption side. So we should be reducing those disruptions via the pod disruptions budget. And this is particularly useful if the init container code is running for long, though we try to keep the duration as short as possible. The third takeaway is about gracefully exiting the init container. We know that the main containers don't start until init container completes successfully. At the same time, any abrupt termination of stateful workload should be avoided because then it can lead to data corruption. So with this, I would like to thank you for your time. Thanks for listening. And if you want to learn more about our engineering systems, you can visit Yelp's engineering blog. Along with that, career opportunities at Yelp you can explore on our careers page, which is yelp.careers. And yep, there is the QR code for giving the feedback. And if we have some time, I think we have a couple of minutes, we can take some questions.